So today's topic is about applications of Gauss law, case 5, that is electric field due to a uniformly charged spherical shell. In that we have three cases. So first we will see two cases, later on the third case. At a point outside the shell, that is small r is greater than r. Consider a uniformly charged spherical shell of radius r and total charge q. So, here you can see this is our spherical shell. Okay, the radius is r and inside that you have a charge q. Now we are considering a Gaussian sphere whose radius is r. That means the Gaussian sphere radius is small r and the shell, which is also spherical in shape, the radius is r and the charge enclosed by that spherical shell is q. So we know by Gauss law, that is integral over closed surface E vector dot dA vector is equal to q by epsilon naught, that is charge enclosed by that surface. Okay, this is by Gauss law. Now, that is, we know that the electric flux is equal to integral over a closed surface electric field vector dot product with dA vector is equal to charge enclosed by that surface. In this case, it is a spherical surface divided by epsilon naught. So the electric field lines and the radial vector both lie in the same direction. That means if you are considering the point P, since this is positive Q, the electric field will come out like this, E field. And the radius vector is also in this direction. Therefore, the angle between them, if you consider a small area dA, the unit normal perpendicular for that small area will be in that direction. So cos 0 is 1. Therefore, magnitude of E and magnitude of A. Okay. So E, electric field all around is same. If you consider each and every point over the sphere or small area dA area over the sphere, it is going to be same in all direction. So having said that, we have E as constant integral over the closed surface. Here is a sphere into dA. So we are considering the Gaussian surface. That means the spherical shell is here and we are considering a Gaussian sphere outside the shell, which is equal to q by epsilon naught. That is charge enclosed by the Gaussian surface divided by epsilon naught. Now integral dA over the closed surface. Now here we know the surface area of the sphere. Surface area of the sphere is 4 pi r square. That means this value is a sphere whose radius is small r. Therefore, the surface area is E into 4 pi r square, which is equal to q by epsilon naught. Now keep this E here, electric field. You bring this term to the other side. So 4 pi epsilon naught. There's r square in the denominator and you have q. This is the electric field that is emanating from the charge q when we consider a Gaussian sphere outside a spherical shell. Now we want to represent this in vector form. E vector is equal to 1 by 4 pi epsilon naught q by r square r cap. R cap is in the direction of radius vector. So this is case 1. Now case 2. Now we are interested what happens if the same Gaussian surface moves and comes exactly on the surface of the spherical shell. That means this capital R and the small r both are equal. Now we are considering for the surface. So in this equation, what you have to do is you have to replace that small r by capital R, which is nothing but the radius of the spherical shell. So if you put r here, then E vector is equal to 1 by 4 pi epsilon naught q by divided by r square into r cap. R cap is the unit normal vector in that direction. Now we will move on to case 3. Case 3 is about what happens if the Gaussian sphere lies inside the spherical shell. So that is case 3 in this subdivision. So now we will see about a third case in the same topic at a point inside the spherical shell. That means this small r is less than this capital R. This capital R is the radius of the spherical shell and small r is the radius of the Gaussian surface that lies now inside the spherical shell. That's the meaning. So we have drawn here, that is, this is the actual spherical shell whose radius is r. Inside we are considering a Gaussian sphere whose radius is small r. That means the radius of Gaussian sphere small r is less than capital R. Okay, now the point of consideration is P. So we know by Gauss law the electric flux emanating from a closed surface is equal to integral. We are considering the entire surface. E vector dot dA vector is equal to charge enclosed by epsilon naught. But now since the Gaussian surface does not enclose any charge, therefore Q value is equal to 0. If Q is 0, then this overall electric field is 0. So electric field equal to 0. So what's the conclusion of the third case? If you consider a small spherical shell and inside that you considering a Gaussian surface whose radius is small r and that small r is less than the capital R. Therefore what happens, since it does not encloses any charge, Q value equal to 0, therefore electric field is also 0. Now we will see the response curve. So we plot a graph between small r and electric field because of this distance r, so ER. So from 0 to r, that means slightly less than r, when r, small r is slightly less than r, up to that the distance is inside the sphere. So inside the sphere the electric field is 0, so the line goes like this. So when r equal to r, we have the relation, so this will become r, so 1 by 4 pi epsilon naught q by r square. But once you increase, so it has some value, definite value ER. So this point is set when r is equal to r, you get some electric field at this point. But later on what will happen? When the radius starts increasing, the denominator term starts increasing. So if the denominator term is increasing, the electric field is decreasing. So the electric field starts decreasing in this way. So ER, so this side of the graph, r greater than that, r small r greater than capital R is ER is equal to 1 by 4 pi epsilon naught q by r squared. So it is a decreasing. Whereas this side, if you see, the electric field is 0. So what is the significance of this graph? From 0 to this point, it is inside. The Gaussian surface is inside the spherical shell. Whereas from r to small r up to infinity, the Gaussian surface is outside the spherical shell. So what happens is it is decreasing. Okay. So that's all about applications of Gauss law. We have covered the entire applications of Gauss law. Major topics have been covered. Thank you for your attention. Thank you.